Well, good morning. This is 11:30, now 11:31 on Thursday, the 23rd of January 2020. It's supposed to be linear algebra class, and right now I'm the only one in the room, so hopefully some of the others will be showing up soon, I hope. I won't go over any announcements because there's no one here to hear them, but we'll just pick up where we left off last time. A couple things. Straighten out here on my desk, and then we'll be ready to go. Okay, I believe last time we're still in Chapter 1, Systems of Linear Equations, and Section 1.2, which is Gaussian elimination and Gauss-Jordan elimination. So far we've done Gaussian, okay? And we have done, last time we did systems of equations that you had one solution, and I think I can't remember if we've done any with Gauss elimination that you had multiple solutions. We'll get there. Let's do example 6 now, and we'll see how it goes. Here they are. I was hoping they would show. I lost my pen. There it is. 100% attendance, what I love to see. Okay. What's that?
No, I was quoting the movie.
Oh, okay. Let me switch on the projector. Switch my lights. Okay. And while we're waiting for the projector to come on, have I made these announcements to you about the college transfer days coming up on February the 12th and 13th, and this really excellent sounding research experience for undergraduates at University of Illinois, University of Arkansas, and Howard University. It's a great deal. You don't see many deals this good. You get top of the art, state-of-the-art exposure, and they pay you to do it. $5,000 they pay you to do it for 10 weeks in the summer. They house you, they feed you, and they give you air transportation there and back once. Okay? Quite a good deal. Deadline for that one is February 15th, so don't forget that. Okay, I was just starting to do example 6. I went over a little bit of what we did last time. Let's do example 6. Here is a system of equations. Let me get my pen set up. Okay. X sub 1 minus x sub 2 plus 2x sub 3 is equal to 4. Okay. X sub 1 plus x sub 3 is equal to 6. 2x sub 1 minus 3x sub 2 plus 5x sub 3 is equal to 4. And 3x sub 1 plus 2x sub 2 minus x sub 3 is equal to 1. Now, what would be your approach to go about solving that system of equations? Anyone want to graph them? Please say no. Okay. Anyone want to do substitution on them? I think I want you to say no there too. Okay. How about elimination by addition? Probably not. Okay. So what do we do? as a augmented matrix? That sounds like a capital idea. What would that be? Got it?
1, 0, 1, 6.
Got it?
2, negative 3, 5, 4.
Got it?
3, 2, negative 1.
Got it. Okay. Now, what would you, when you get a matrix set up like this, what's the first thing you want to be the case? Up or left to be a leading one. We've got it already. Don't have to do a thing to it. Okay? Now, what do we want to happen next? By the way, we're still doing what they call Gaussian elimination. Zeros below it. And how would you get that first one to be a 0? Yeah, minus row 1 plus row 2 is the new row 2. Okay? So since we're using the first row, write it down. 1 minus 1, 2, 4. Okay? Now, we're changing the second row, so what would that become? 0. 1. Is that what you said? Wait. What's the third one? Negative 2 plus 1. Negative row 1 plus row 2. Negative 1, okay. The fourth entry? 2. Okay. Just to save a little on space here, I'll pull that bracket in just a tad. Okay, hopefully I'll get one more square out of it. Okay, what do we want to happen next? Zero below that 2 to become a 0, so how do we make that happen? Okay, say that one more time.
Row 1 plus 1, row 2 minus 1, row 3.
Okay. You may be saying it right, my hearing's so terrible. Say it a little louder.
Row 1 plus row 2 minus row 3.
Ooh, I don't. Okay. Interesting. Will that work here? It may. However, it's a little bit easier than to do that, I think, to just do a minus 2 row 1 plus row 3 is the new row 3. Now, I think what you said would work. It certainly should work. But keeping up with adding and subtracting and stuff like that, and doing all 3 rows, they usually like to use the leading one to eliminate other things. So that's why they like to do this. I think what you said might work. I think it would work. But let's do it this way. What would that be? 0. A little louder. Second. Okay, negative 2 times negative 1 is
2.
Plus 2 minus 3 is negative 1. Okay, next. One. Good. Next. Negative 4. Okay. Then what would we like to happen next? want that 3 to become a 0, and how did you say to do that? Okay. Are you saying add 2 and 3 and subtract 4 or something like that? That's what you did the last time. It may work, but usually what they like to use is that leading 1. Minus 3 times row 1 plus row 4 is the new row 4. Let's try that and see what happens. What do we get?
Oh, so you can't work on the row one.
What's that?
You can't do the same row twice. You have to use it.
No. I think you can. I don't think there's any problem with it, except that their preferred method is to always use that leading 1 to eliminate everything else. There are times when you can do other things, and what I think you were recommending probably would work. With what you were saying, add those 2 and subtract this. That probably would work. It's just keeping up with the signs and stuff. It seems like there's more potential for error there, but maybe not. Let's try this one, see what happens. But they like to use that leading 1. That's why they got it there. So what would that give us? Minus 3 row 1 plus row 4. 0. Okay. Really? Minus 3. 5. Okay. Next. What's that? Now maybe I wrote it wrong, so make sure I haven't made a mistake here. Huh?
I haven't looked at the book yet, so I'm not sure.
Yeah.
I was copying it down wrong.
Okay. Because I have been known to make errors many times. Okay. Next. Negative 7. Next. Negative 11. I'm not liking that last row at all. Sort of almost wishing there was something. Nope, that seems to be what they got. All right, what do we want to happen next?
Row 3.
Even before that, okay. What you wanted first was the first entry on row 1 to be a 1. We had it, then we made 0 below. So now we move to row 2. The first non-zero entry there, we want to be a 1. It's already there for us. We're happy. Okay, and now we want what? 0 below it. Okay, so how do we make that negative 1 become a 0? Row 2 plus row 3 becomes a new row 3. All right, let's see if we can squeeze it in over here. I think we can. We've already used row 1. We're not going to mess with it anymore at this point. So it's 1 minus 1, 2, 4. Next. We're using row 2, so leave it alone. 0, 1, minus 1, 2. Now, new row 3 is what? 0, 0, 0, negative what? 2 minus 4 is? Did you say 2? Negative 2. Hold the presses. Stop right there. What does that third row tell you right now? That 0x1 plus 0x2 plus 0x3 is equal to negative 2. How often can that happen? Never. This is an inconsistent system. It can't happen. a solution. You don't have to mess with that next row, which I didn't want to anyway, because that line right there, because these represent x1, x2, x3, and your constant. No way that would ever happen. Stop right there. This is an inconsistent system. There's nothing you can do with it. Okay. Now, no reason to eliminate anything else. Done. That can't happen. All right. Any questions on that? Now, what is a little bad is the fact they didn't give us any with infinite number of solutions that I recall. The previous one had a one and only one solution, and it was a way back before. In fact, it's been a while since we had one with infinite number of solutions. So we'll run into them later. But let's move on to Gauss-Jordan elimination. Gaussian elimination was getting row echelon form, which is the leading non-zero entry in each, well, all zero rows are at the bottom, if you have any. The first non-zero entry, well, the first non-zero entry in each row should be a 1, and those are called the leading ones, and the leading one should step to the right at least one space every time you go down a row. That's what row echelon form is. So you have a leading one with zeros below it, leading one, zeros below it, so forth. Now we're doing Gauss-Jordan elimination. With Gauss elimination, you apply elementary row operations to a matrix to obtain row equivalent row echelon form. The second method is called Gauss-Jordan elimination after Carl Friedrich Gauss, same guy, and Wilhelm Jordan. Okay, sounds like a good German name. Who came along many years after Gauss had died, I'm pretty sure. Let me see if I can recall that. Yeah, Gauss was, well, no. Jordan was 13 years old when Gauss died, so they were alive, but I don't think they really collaborated much. Old man of Gauss's stature collaborating with a 12 or 13-year-old, I don't think that happened. Okay, but Jordan came along and came up with something else. Continues the reduction process until a reduced row echelon form is obtained, and this is illustrating that. Now, example 7, you can go to larsonlinearalgebra.com for an interactive version of this type of example. Now, I'm almost certain that that's new with this new book. I don't recall this being in the previous edition. So he has come up with a larsonlinearalgebra.com that you can use like you do in some of his other texts. He still doesn't have the calcu.com for this book. Okay, I don't know if he'll have it in the future, but he doesn't now. So let's do example 7. And we'll see the difference between Gauss elimination and Gauss-Jordan elimination. Okay? Here's your system of equations. X minus 2y plus 3z is equal to 9 minus x plus 3y is equal to negative 4, and 2x minus 5y plus 5z is equal to 17. Now, I'm not absolutely certain, but I think this is looking familiar enough. I would say we've probably done this a time or two before. But it's okay. We're going to do it with Gauss-Jordan elimination. So what's your first step? Get it into a matrix. And what would that be? 1, negative 2, 3, 9, negative 1, 3, 0, negative 4, 2, negative 5, 5, and 17. Okay. What's the first thing you want to happen? Upper left to be a 1. We already got it. We don't have to do a single thing to make that happen. We're happy campers. What's the next thing we want to happen? Yes, the 0 in both of the rows below it. Let's deal with the first one first. How do we make that -1 a 0? Row 1 plus row 2 becomes the new row 2. All right, I think we can do that fairly easily. So we're going to write down that first one. 1, negative 2, 3, 9. And then the new second row becomes 0, 1, 3, 5. Okay. Next, what do we want to happen next? At 2, we want to become a 0. How do we make that happen? Becomes the new row 3. Okay, so let's do it. What do we get? 0. Good, that's what we wanted. Negative 1. Negative 1. Wait. Yeah, negative 1. I went to the next one, yeah. And then last is negative 1. I was doing that one. I said, wait a minute, I skipped one, but all of them were negative 1. All right, what do we want to happen next? Here is where things change ever so slightly. Well, the very next thing is the same. We have a 1 here, now we've got 0s below it. Next thing we want is the leading non-zero in row 2 to be a 1. We already got it. Here's where things change. Gauss-Jordan elimination, we want a 0 above and below, not just below. Okay? Just below would be row echelon form. Above and below would be reduced row echelon form. Okay? So, once we finish that first row, we're through with it. Okay? We never mess with it again once we got that leading 1 there. Here we do mess with it. So how are we going to get that negative 2 to become a 0? Hint, use your leading 1. Two times row 2, add it to row 1, and you get a new row 1. Okay? So now we are messing with row 1. Before, once we finished, we weren't doing anything to it. So let's do what you just said. What do you get? 1. 0. That's why we did it. Okay? 9. 19. This isn't looking very nice, is it? Now we're using that leading 1 in row 2, so this one we just write down. 0, 1, 3, and 5. Okay? What's the next thing we want to happen? Okay. That negative 1 in the third row, the first one to become a 0. So how do we make that happen? Row 2 plus row 3 is the new row 3. Okay? And what do we get here? 0, 0, 2, 4. Okay. All right. Just a quick recap. You wanted a 1 here. We had it. We got zeros there, we got them. We wanted a 1 here, we had it. 0 above and below, we got it. What's the next thing we want? A 1 in the first non-zero entry in row 3. How do we make that happen? Oh, don't mess with any other row, just row 3.
Multiply by 1/2.
Multiply by 1/2 or divide by 2, either one. Okay? Now, if it's okay with you, I'm just going to do it right here. This will become a 1, what? 0, 0. You divide that row by 2. 1, 2. So I'm going to just do it so I don't have to write all those numbers again. 0, 0, 1, 2. All right, good deal. Now we've got a 1 in the first non-zero entry in row 3. What's the next thing we want to have?
Back substitute.
No, we would do that in Gauss-Jordan. In Gaussian elimination, we do back substitute. Here, we get zeros above. Remember? Gauss-Jordan built zeros above and below the 1s. So now we want the 9 up there to become a 0, and then the 3 to become a 0. Then, no back substitution is required. So let's try it. What do we do to make that first happen? We want that 9 to become a 0. Using the leading 1 in row 3. How do we use it? -9 times row 3 added to row 1 becomes your new row 1. All right, let's do it. -9 times 0 is 0 plus 1 is 1. -9 times 0 is 0 plus 0 is 0. And go on. 0, 1. That worked out nicely. Those big numbers disappeared. What's the next thing you want to happen? 3 to become a 0. How do we make that happen? -3 times row 3 plus row 2 is a new row 2. Okay? -3 times 0 is 0 plus 0 is 0. -3 times 0 is 0 plus 1 is 1. Continue. Zero, that's exactly what we wanted. -1, and then we write down the last row. 0, 0, 1, 2. Now, one of the big advantages of doing this is, as we said before, there's no back substitution involved. Now you can just read across here. X is equal to 1, Y is equal to -1, and Z is equal to 2. Okay? No back substitution required. Now the other advantage of Gauss-Jordan elimination is you wind up with that as a coefficient matrix. What is that? Have we named that yet? I'm trying to recall. Probably not. Okay. That has a special name. A square matrix with 1s on the diagonal and 0s everywhere else is called the identity matrix. Okay? And that's going to be very important in what we're going to do either next or soon. Okay? And that's what you want to happen. Now, it may do that when you start tooling along here, you may wind up with a row of zeros at the bottom. If so, this would have been infinite number of solutions. Or it may have been you would have gotten a 0, 0, 0, 2, or negative 2, or pi 16, or something like that. You'd have gotten that, no solution. But as long as you get that identity matrix with, and it doesn't matter what numbers are here, that has a unique solution. So, like I said, we didn't do any in the Gauss elimination that showed you how to get infinite number of solutions. But it would have been the same deal. The row of zeros at the bottom more than likely was going to make that happen. All right. So, what your solution here is x equal 1, y equal negative 1, z equal 2. Okay. And if you go back, you'll see we did this very same problem with Gauss elimination. You did back substitution, got the same answer. Okay. Now, they have a little thing at the bottom of the page here. The elimination procedures described in this section can sometimes result in fractional coefficients. Unfortunately, true. For example, what if we had this as a system? You want me to erase what we got now or leave it? Okay, so what if this was our system? Okay, we'll just pretend that's not there. 2x minus 5y plus 5z is equal to 14. 3x minus 2y plus 3z is equal to 9. Minus 3x plus 4y is equal to minus 18. Okay. Now, I'm sort of sorry that Josh had to step out, because this is one that he probably would have seen something and wanted to do. Okay. Now, what's ugly about that system? Maybe several things ugly about it. What's the first thing you want to happen? A 1 in the upper left. There's not one. Moving rows around, is it going to make one happen? Just, yeah. No way to get it easily. Now, the next thing I look for when this is the case, see if dividing one row, any of the rows, is going to produce a reasonably good thing to work with. Well, dividing by 2 will make that a 1, right? This will be a minus 5 halves, 5 halves, and 7. Two fractional forms, can't avoid them. Dividing this by 3 would make minus 2/3, 1, and 9. Hey, I actually like that a little better. Dividing this by 3, or negative 3, would make a 1, a minus 3/4, and a 6. Sort of, I like that bottom one best, okay? So I would be tempted to flip the first and the third rows, interchange those two, and get this one on top. Well, this is something I was imagining you might be suggesting too. Before I go too much further, I want to go on and add these two rows together. That's going to eliminate the x. And you can do that. That is legal in most states, so you can do that. So the first thing I think I would do is swap these two rows with this one on top. Okay, then I would add these two rows. This one's up here now together and get a 0 here, and not do. That's before I make any fractions anywhere. And then I would divide this one by minus 3. Okay. They're not suggesting you do that. They're saying go and divide by 2. That's fine too, but try to make life as easy as possible. I'm all in favor of minimizing work. I'm that lazy, so. But they don't carry it any further. And well, maybe they did say that. It said, you may be inclined to multiply the first row by -1 to produce a leading 1, which will result in working with fraction components. Sometimes judiciously choosing which elementary row operands you apply and the order in which you apply them enables you to avoid fractions. So that's why I said maybe that other method might be a little better. Okay? They just leave it there. They don't carry it any further and show you what they would prefer you to do, but that was their suggestion. All right. The top of page 20 is then a discovery, and sometimes these are pretty fun and instructive, and sometimes they're a pain in the neck. Now, here is this discovery. Without performing any row operations, explain why the system of linear equations here, 2x1 plus 3x2 plus 5x3 is equal to 0, minus 5x1 plus 6x2 minus 17x3 is equal to 0, 7x1 minus 4x2 plus 3x3 is equal to 0. Now, when at first glance, this looks like something a lot like we were talking about at the bottom of the previous page. There's no leading ones here, and no really particularly good way of getting them. This will produce two fractions here. This will produce two fractions there. This will produce two fractions there, if you divide by 2, -5, or 7. So this doesn't look particularly handy. But before you do any of that, all they're asking is, can you tell me whether that's a consistent system or not? Now, you'll need to refresh my memory on what is a consistent system. Has at least one solution. At least one solution. It may have an infinite number of solutions, but it's going to have at least one solution. Can you guarantee that with that system? Here's the dead giveaway. If x1, x2, x3 is equal to 0, I guarantee every one of those equations is equal to 0. If that is, and this is called a homogeneous or homogeneous system. Anytime you have that, all these are equal to 0, you know it's going to be 3 equations, 3 unknown, it's going to work. Because x1 equals 0, x2 equals 0, x3 equals 0, guarantees that has a solution. Okay. Now, not too much there, but now, here's another one. I'm going to cheat. If I had looked ahead, I wouldn't have had to cheat it, but it wasn't too bad. Take this one and add 2x to the 4th equals 0. This one and add or subtract 3x to the 4th equals 0. And this one add 13x to the 4th and have it equal to 0. Now, in this one, we have more variables than we have equations. Now, I want to say always, but quite often I want to say never, okay? But just about any time you have more variables than you do equations, you're going to get an infinite number of solutions. I think that's safe to say always. But is this going to be consistent or inconsistent? is still consistent because 0, 0, 0, 0 works, and you're going to have an infinite number of solutions, so that's just one of infinite number. The first one, 0, 0, 0, may have been your only solution, or it could have had an infinite number. But there was no way it was going to have no solutions. And this one, no way it'll have no solution, and this one's guaranteed to have infinite number of solutions. System below has more variables in the equation. Why does it have an infinite number of solutions? Because if you did a Gauss-Jordan elimination, you can't possibly come up with a row of zeros on the left equaling something that's not 0 on the right, so you're always going to have solutions, but this one will always have a variable without a leading one. So therefore it's going to be a parametric equation. All right. Now, I'm going to do a little bit simpler one than that, but here is a system of linear equations. 2x1 plus 4x2 minus 2x3 is equal to 0. 3x1 plus 5x2 is equal to 1. Now what they tell you to do, solve the system, that system of linear equations. What would be your first step? Put it as a matrix. What would that be? Second? Okay. Now wait. I'm lazy enough. I want to also do something else. Notice that first equation. What can you do with that? Divided by 2. You're lazy, aren't you? Okay, good. All right. All right. Divide by 2 to begin with, and that saves us a step. Okay, so what would that give you? 1, 2, negative 1, 0. Next, 3, 5, 0, 1. I can't think of anything to do with that. Okay? Now, by dividing by 2 in that first equation, we wound up with a leading 1, which is what we wanted. Thanks for being lazy. Okay. What's the next thing we want to happen? 0 below it. I think that came out. And how do you make that happen? Negative 3 times row 1. Add it to row 2, and you get the new row 2. All right. So this becomes, and again, yuck. Again, we leave the top row alone because that's the one we're using. 1, 2, minus 1, 0. And your new second row will be 0, negative 1, 3, 1. Okay. Next. Okay, you want that negative 1 to become positive. How would we make that happen? Perfect. Now I'm going to do that real lazily. Make that a plus, minus, minus. Done? Okay. All right. Now, what's the next thing we want to happen? 0 above that new leading 1. And I don't have enough room, I don't think, but it's okay because this isn't going to take much longer. What will this be? We're going, okay, how do we get that 2 to become a 0? Plus row 1 is the new row 1. Okay, we're using the bottom equation, so we're going to leave it alone. 0, 1, negative 3, negative 1. New top equation is 1, 0, 5, Negative 2 is, no, what? 2. Okay, that's what I thought. 2. Okay, now, if you recall, okay, we've done Gauss-Jordan elimination. You don't have to have what we call identity matrix here, but you have pretty close to one. The trouble is this row isn't included, but you've got everything reduced here. You can't go any further. So now you are going to do back substitution, but here we assume a parameter for that third one. Because you can't solve this, so make that a parameter. What's our favorite parameter? Yeah, hopefully we'll come back. There we go. What's usually the favorite parameter? T. They use S and T a lot. Sometimes R, whatever you need. T is their favorite, but you don't have to use T. You can use any letter other than X. Okay, don't use X, that's in the problem here. Okay, so the column with no, now don't count your constants. Don't mess with those. But your column of variables that doesn't have a leading one, let's let that be T. So basically what we're saying here, let x of 3 equal T. Okay? Now, you tell me what that first row says. No, there's no y in there. X of 1. This row right here. Plus 5t is equal to 2. So what's x of 1? 2 minus 5t. Right? Now what's that second row telling us? X of 2 minus 3t equal negative 1, and that implies that x of 2 is equal to 3t minus 1. Okay? And, of course, we know x of 3 is equal to t. So, make sure they got it right. They wrote it differently, but they got it right. For t is any real number that's a parametric form, and any variable that doesn't have a non-leading, doesn't have a leading one, then will be your non-leading variable, and that's going to be parameterized. Okay? So here's what we've got. You can just write it like that, or you could write it as an ordered triplet, being 2 minus 5t, comma, 3t minus 1, comma, t. And any t you choose, 0 would give us 2 minus 1, 0. That should work. Okay? 1 would give us negative 3, 2, 1. Negative 1 would give us 7, negative 4, negative 1. Okay? Any t you want to choose, there's an infinite number of solutions. Okay? Make sense? All right. Next concept is what we were hitting on in the discovery. Okay? Now, I gave you the name before they did, so shame on me, but here's what we're talking about. Systems of linear equations in which each of the constant terms is 0 is called homogeneous. Now, I don't know if that's called homogeneous or homogeneous. I'll use them interchangeably because I've never, that I recall, heard them pronounced. So I don't know what's the right name for it, homogeneous or homogeneous. When I think of homogeneous, I think of homogenized milk. So I usually say homogeneous to keep from thinking about homogenized milk. But that's not a good excuse, okay? So here's what a homogeneous system of equations, M equations and N variables would be like. A1, 1, 1. That's sort of ugly. Okay. A sub 1, 1, x sub 1 plus a sub 1, 2, x sub 2 plus a sub 1, 3, x sub 3 plus dot, 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 all the way up to a sub 1 n, x sub n is equal to B1, I think it is. No, I'm sorry. This is homogeneous or homogeneous. That will be 0. Okay? That's the whole point of this. 0. Okay? The next equation, you tell me. Would be your first coefficient. 2, 1. X1 plus next right plus dot 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 plus a sub 2n x sub n is equal to 0. Let's do one more. A sub 3, 1, x sub 1 plus a sub 3, 2, x sub 2 plus a sub 3, 3, x sub 3 plus dot, dot, dot. My writing's getting worse and worse. Plus a sub 3 n x sub n. My screen is flopping around on me. That's equal to 0. Now let's just dot, dot, dot our okay, what would be the last one? A sub m1 x sub 1 plus a sub, that's ugly, m2. I can't get it to right. Wait. Okay. A sub m2 x sub 2 plus a sub m3 a sub m3. Okay. I don't know where that came from. Yuck! Okay. A sub m3 x sub 3 plus dot, dot, dot plus a sub m n x sub n equals 0. Okay. Sorry. I think I've been writing over this fan that cools my computer so much. My eyes are so dry I can hardly see out of them. Okay. Now, there is your system of equations. Every constant on the right is a 0. And here's the keys. We've already hit this in discovery. A homogeneous or homogeneous system must have at least one solution. Specifically, if all the variables of a homogeneous system have the same value 0, each of the equations is satisfied. That solution is called the trivial or obvious solution. Okay? Now, depending on how many equations, how many unknowns, and what they work out when you do all your elimination, you may get that's the only solution. You may get there's an infinite number of solutions, but in this case you cannot get that there's no solution, because you know there's at least one. Okay. Now, let's go to, how are we doing time-wise? 20 minutes? Good. Okay, I thought it should be about that because we have 55 on the clock here, but I couldn't remember if we got started right on time. I guess we did. Example 9. Solve the system of linear equations. X sub 1 minus x sub 2 plus 3x sub 3 is equal to 0. 2x of 1 I've lost, there it is, plus x of 2 plus 3x of 3, and that one's equal to 0. Sorry. Writing's getting worse, my throat's getting worse, everything's getting worse. All right, what's your first step? Write it as a matrix, and what would that give you? 1 minus 1, 3, 0. Next, 2, 1, 3, 0. All right, there's your matrix. Now we're doing Gauss-Jordan here. So what's the first thing that we want to be the case? Upper for 1, we already got it. We're happy campers over that. Next, we want 0 below it. How do we make that happen? Negative 2, row 1 plus row 2 is the new row 2. All right. So we're using that top equation, or top row, so we're not going to mess with it for now. We'll later, but not now. 1 minus 1, 3, 0. What's your new second row? 0. 3, you said? Okay. Negative 3. And 0, of course. That last one's going to be easy every time. Whatever you do to it is going to be a 0. Okay, next. Okay, how do we make that happen? Divide everything in that equation by 3, and I'm going to be real lazy about it. And what would be the result of that? Divide everything in that equation by 3. 0, 1, minus 1, 0. So this will be a 1 and a minus 1. Okay. I didn't have to do it that way, but I just thought, why not? Okay. So, oh boy. 1 and minus 1, right? Okay. Took too long to change my pen. I want to make sure I had it right. Okay, next thing we want to happen. Okay, we got a 1 with a 0 below it. Next row, leading non-zero entries of 1. What do we want to happen now? A 0 above it. How do we make that happen? Okay, row 2 plus row 1 is a new row 1. Okay, now let's see if we can squeeze that in here, though it's not necessary. We're not going to need that much more room, but what do we get? 1, 0, 2, 0, and the second row? 0, 1, 0, 1, 0. Okay, just like we had it. All right, we've done Gauss-Jordan elimination as far as we can go. I can stand up. Oh, all right. What do we do now? Okay, which one? X of 3. Believe it or not, it won't always be the x of 3, but quite often it will. So we'll let x of 3 equal, you happy with t or want something else? Okay, coffee? Never mind, okay. Let that be our t. All right, what does the first row tell us then?
One is equal, x is equal to 2t.
Is equal to
1 is equal to 2t.
is equal to negative 2t? Okay, negative 2t. And the second row tells us
X of 2 is equal to 1.
t. Right? All right. So here's our ordered triplet, if you want to write it that way. Negative 2t, t, t. You might need to go to the bathroom. Okay, never mind. Okay. All right. That's your... Let's see, where was here? Yeah, here we are. Negative 2t, t, t. Okay. That system has infinitely many solutions, one of which is 0, 0, 0. T is equal to 0, is 0, 0, 0. T is equal to 1, it's negative 2, 1, 1. And T is equal to minus 1, it's 2, negative 1, negative 1. There's an infinite number of solutions. Okay. So as illustrated there, a homogeneous system has, with fewer equations than variables, will always have infinitely many solutions. Okay? And that leads to a theorem. I think I'll write it down here since we got room. Every homogeneous system I'm not going to write it all out. System of linear equations okay, is consistent. Okay, we saw that in the discovery. Moreover, if the system has fewer equations I can't write. If the system has fewer equations than variables, it must have infinitely many solutions. I don't know why it does this. It has to get its mind back. Okay. It must have infinitely many solutions. Because no homogeneous system can't have no solutions. It's either going to have one, the trivial solution, or an infinite number. Okay? And they say example 9 is going to help you prove that. That finishes 1.2. Homework exercises here. Be any of the odds 1 through 5. They're all at Calc Chat. Either 7 or 9. They're both at Calc Chat. Any of the odds 11 through 17. They're all at Calc Chat. 19 to 23. They're all at Calc Chat. 25 through 37, they're all at Calc Chat. Big ones here, 39 or 41, they're both at Calc Chat. 43 or 45, they're both at Calc Chat. 47's at Calc Chat, or should be. 49 should be at Calc Chat. 51 should be at Calc Chat. 53 should be at Calc Chat, 55 should be at Calc Chat, 57 should be at Calc Chat. That's a writing thing. True false is 59 at Calc Chat. 61 should be at Calc Chat. 63 should be at Calc Chat. 65 should be at Calc Chat. 67 and 69 should be at Calc Chat. All right. Let's move on. Do we have time? Yeah, I think we do, don't we? 10 minutes? 9 minutes. Okay. Let's move on to 1.3. I think I'll clear the screen. And, okay, these are applications of system of linear equations. Now, I'm not going to go over these with gory detail. They can be very time-consuming, but they're all doable. Most of the time we get computers to do them, but one of the things is polynomial curve fitting, okay? What if we had, I think I'll go to a different slide. What if we have endpoints in the xy plane? So say we have a point there, 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 and there. Okay? Now, that's 1, 2, 3, 4, 5, 6 points. Now, if you want to find the polynomial function of degree n minus 1 whose graph passes through all those points, that's called polynomial curve fitting. Okay? Now, it can be tedious. In fact, I think I have 7. This is this 1, 2, 3, 4, 5, 6, 7, 10. It can be a bit tedious, and the more you have, the more it is. So you can come up with a 6th-degree polynomial that will go through every one of those points. Anything fewer than that number of degree polynomial may occasionally happen, but generally not. Any higher degree, not necessary, but you can make anything higher degree fit too. But you'll usually reduce to a 5th-degree polynomial. Right? 6th-degree polynomial. So we have 7 points. Okay. Now, how would you do that? Okay. First, we're going to assume a 6th-degree polynomial. So, a sub 1 x to the 6. Okay, let's call it a sub 6. A sub 6 x to the 6 plus a sub 5 x to the 5th plus a sub 4 x to the 4th, blah, 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 on down, plus a sub 0, which has got an x term, is equal to some constant. Okay. Now, what you can do then is get your xy point for each one of those. This would be a minus 1, 2, 3, 4, 5, 6, positive 1, 2, 3, 4, 5, 6. So, negative 6, 6, you know is on that curve. Negative 4, negative 1 is on that curve. Negative 2, 3 is on that curve. 0, negative 3 is on the curve. 0, negative, 3, negative 2 is on the curve. And yeah, you get the idea. Okay? Now, so then take each ordered pair, and wherever you have an x, remember you had x to the 6th, that would be a negative 5 to the 6th, no, negative 7 to the 6th, or whatever that number was. So you wind up with a series of equations, and by the way, the equal sign over there, that's going to be the y value, right? So you have some really big numbers because you're raising it to the 6th power, some pretty good sized number, but you have a system of equations and you have 7 unknowns. A sub 6, a sub 5, a sub 4, a sub 3, a sub 2, a sub, down to a sub 0. So that's a total of 7 unknowns. Your coefficients are now your unknowns. And you do that equation, an equation like that for every point you have. And then you do load reduction. Yeah. Okay, if you think of the size of those numbers, those are going to be incredible. Okay? That's why you have a computer do it. Okay? Because it can do it without as much. That's called polynomial curve fitting. Okay? Now they actually turn it around and do a sub 0 first plus a1 x1 plus a2 x squared. That actually probably is going to be a little bit better because at least one of these, that's going to be a -1. So you're a lot more likely to have a leading one coefficient than if you did it the other way. So the numbers should be smaller anyway. All right. They do a polynomial curve fitting with 3 points. That's going to come up with a parabola. You can look at that to your heart's content. Now, actually, example 3, you can go to LarsonLinearAlgebra.com for an interactive version so you can watch them do it. They've got 1, 2, 3, 4, 5 points, so they come up with a 4th degree polynomial. And it's going to be a pain, but it's not too bad. And by doing the a sub zeros first, you guarantee those coefficients are all going to be 1. So at least that first coefficient is not too bad. Now, example 3 is going to be translating large X values before curve fitting, which sounds like a great idea. And that gives you years and values, and they just do a transformation of the X rather than doing 2011, 12, 13, 14, and 15. Just take that middle one, 2013, and then subtract that from all of your X values. That gives you a -2, -1, 0, 1, and 2. Okay. Really turns in, still can be a pain in the neck. At the end, you've got to go back and change back. Okay. Example 4 is another application of curve fitting. And it's an astronomical example. And you can fiddle with that if you'd like. They show you something else you can do by taking the natural logarithm of those distances and then doing a curve fitting there, and that gives you something pretty neat. All right. Not going to do much more with that, except I will mention the linear algebra applied. How are we doing on time? Got 1 minute? Researchers from Italy are studying acoustical noise level from vehicular traffic at a busy 3-way intersection. That's, guess what? They use linear algebra to analyze that. So I think we'll wait till next time to do our network analysis. But if we got a minute, I'll just explain what we mean by a network. So I think I'll go back to the other slide. If you have input, a node, and output, okay, then if you know you got 25 coming in and you got x sub 1 and x sub 2 leaving, you can write that as a linear equation, right? X sub 1 plus x sub 2 has to equal 25. You can't have a sink there, you can't have a source there, you have to have something. Well, that would be traffic flow problems. That would be lots of things. We'll start next time with example 5, which will be, I thought I had a pencil out here and now I can't see it. Put it back in the drawer, I did. Okay, we'll begin with example 5. Now we will do this one because its numbers are a little nicer than polynomials will be. But also it leads to electrical network, which I think y'all are doing now. Have you gotten to Kirchhoff's laws yet? No. Are you in physics 1 or 2? 2. Okay, you're going to get to Kirchhoff's law, so it may be a good idea to get to this before you get there, because that's a classic example of using this. Example 5 is pretty easy too. So we'll do 5. But Kirchhoff's law is much more practical. So this is practical too. What kind of engineering are you going in?
Electrical.
Electrical. Oh yes. You're going to be doing a bit of that. So once we finish 1.3, I think that's it. Yes, that's it for chapter 1. So I'll be giving you a test next week.
Okay.
Maybe not Tuesday, maybe Thursday. But okay. Good deal.
All right.
Have a good weekend.
You too.